We are ready for the session 6. The resource person is ready with us. Sir, good evening, sir. Sanjaya Kumar Panda, sir. Thank you once again for joining us, sir. Yesterday it was a great session on AI and LLMs and various LLMs, the way they work, the way they support us in the education system, and all. What all you explained, it helped a lot. And we are looking forward for your present session. I hope all the participants enjoy and learn a great deal from this session, sir. I'm handing over the session to you, sir, please.
Yeah, thank you. Thank you very much, sir. So, good evening to all the participants. I hope you are able to see my screen, right?
Good evening, sir.
Good evening. Is it visible? My slide is visible.
Not visible, sir. Not visible.
Is it visible now?
Yes, sir. Yes, sir. It's
Okay,
good,
thank
sir.
you.
Correct.
Thank you. So, I welcome all of you to the second session and my second lecture. So in the first lecture, we have discussed about how AI and LLM can be integrated into the education. Today, I am going to tell you some technical perspective that how actually LLM works behind the screen and what are the importance of this large language model in deployment perspective. So nowadays, it's generative AI and its integration with our day-to-day activities has emerged. So large language model inference service is more important. So what do you mean by inference services here? Suppose in ChatGPT you have written a particular prompt and it is replying to the prompt after 5 minutes. So user will not be happy with that particular inference. Inference means the exchange of query and response between the user and a system. So what we want here that how to improve this particular inference services. If faster inference will be provided, then user will feel satisfaction of that particular response. No one has a time to wait for a longer period of time. And nowadays also, whenever we are giving a particular prompt in a ChatGPT like platform, you know that it is asking you that thinking for a better result. And there is also a option saying that immediately you can produce the result. Means if you have
तो इंडिया वेंट बाय द बुक सारे प्रोटोकॉल्स इंडिया ने माने और उसके
if you have time, then you can wait for a better response. But if you don't have time, then you can go for you can skip that one and you can say that I need immediate result. Such type of options are also nowadays available in the large language model. Now, how to make inference services faster? Suppose we develop a large language model for education, right? And which covers our all type of education, starting from primary to higher education. Then question arises that how we are going to deploy this large language model. Suppose as an individual, like everybody is now attending this meeting through mobile phone or laptop or a desktop. So a desktop and laptop is having limited computational devices, right? Limited computational capacity. We don't have enough capacity to store a large model into our system, and we do not have efficient mechanism to run that particular model in our system because our system is very limited system. So one possible solution is that if I expand my system, now suppose my computational capacity is less. Let's say I am using a 4 GB of RAM and I replace that 4 GB of RAM with let's say 64 of GB of RAM. That makes the inference services faster. Or somebody can say that I am not happy with 512 GB of hard disk or SSD. I want to replace with a 4 TB of 4 TB of hard disk, right? So that way, we are going to enhance the capacity of a computer system to improve the inference services. So, in order to improve the inference services, we need a faster system, right? So, who will provide that particular system? As an individual, if I want to enhance the capacity of my system, it is not possible because I have to afford a lot of amount, right? So it is high cost, it is expensive. Similarly, even if I am using a, let's say, GPU resources, because you know the graphical processing unit GPU is normally used to play games, play different or edit some kind of videos, edit some kind of audios. All these cases we are using GPU, and GPU is much faster than the CPU, right? And GPU resources are not available around the clock. Like if you want to use these GPU resources in Google Colab platform, you have to pay. So you need some resources to run this large language model, right? Individually, you cannot do because you cannot afford it. If you go for ChatGPT, you run that particular model like Google Colab platform, then you have to ensure that the dedicated GPU is given to you. Otherwise, you can face the availability issues also. That's why many people have thought that how we are going to deploy this large language model for education in various platforms. We can go for individual platform, we can go for a centralized platform, or we can go for a distributed platforms or decentralized platform also. So recently, those works are done in this particular field. They focuses on decentralized physical infrastructure network, or called as DEPIN. DPIN will solve the expensive nature, it will provide inexpensive solution, and it will enhance the capacity of the computational devices by providing various GPU resources. So in that perspective, we can run our large language model into such type of particular system like DPIN system. Now, if you want to deploy a large language model, then what you are going to check? Like when I give a particular prompt, I want to check that how faster the platform, like ChatGPT kind of platform, is giving me result. So in order to assess the performance of this ChatGPT platform, we have a matrix called as time for output token. Token means the words that are generated from this particular platform. How much time you are going to take to generate the first token? How much time you have to take from move from first token to the second token to the third token, like third token to the nth token. So I need to calculate the time, because inference services that how faster we can provide the service. In order to judge that which platform is providing you better service, you need to focus on a metric. That metric is called as time per output token. So this matrix is actually calculate latency. Latency means delay, means how much time it is taking to generate each token after the first token. Obviously, if I have given, let's say, 3 different models for AI in education. Let us talk about, let's say, there is a model M1, there is another model M2, there is another model M3. So I want to compare this model and choose one particular model for our education system. So when I compare these 3 models with respect to TPOT, assume that M2 performs better. Then obviously I'm going to prefer M2 model compared to M1 and M3. So irrespective of any type of model, every time our objective is to minimize the execution time. So shorter execution times are always preferable, right? So in order to implement such type of system, many people have come up with a different type of solutions. I'll tell you one by one solution from a very easy solution to a complex solution. Like there are some kind of heuristic. Heuristic provides a better solution in a particular situation. Like you can develop a large language model for many domains. You can develop a large language model for a specific domain. So heuristic will work if you develop a large language model for a particular domain. So in that case, heuristic algorithms are much suitable. Sometimes people take care of the mathematical equations. That mathematical equations, if you solve, it will give you the how the inference is going to be carried out. Like any problem can be converted to a mathematical problem. If I solve that particular mathematical problem, whatever solution I am getting, that I am implementing in the education system, that also I can do. Now, if you see, this picture shows that what is the difference between a CPU and GPU. and why GPU is required for the large language model. Okay, like here you can see this architecture is the very simplest architecture which is used in the modern computer system. In modern computer system, you know, we have a input device and we have a output device. Input is converted to the output through CPU, that is called a central processing unit. And if you see the central processing unit, CPU has two powerful unit here. One is called as control unit, another is called as arithmetic logic unit. Arithmetic logic unit means we are doing addition, we are doing multiplication, we are doing division, we are doing subtraction. These are nothing but arithmetic operations. Control unit is going to give instruction what kind of work is done by the CPU. Whether I want to do addition, I want to do multiplication, I want to read the data, I want to write the data, all these things will be taken care by the control unit. And in order to store, we have a memory unit. So in this case, you can see in CPU case, the amount of focus that given to the control unit, the same thing is given to the arithmetic logic unit. But when you go for a large language model, you have several layers. You have several layers. You have to generate many tokens. That is not feasible in the case of CPU. That's why people are moving from CPU-based system to a GPU-based system. Like here you can see in the CPU-based system, we have control unit and we have arithmetic logic unit. So how I can make a computer system faster? How I can run a large language model faster? I can do this one if I have many ALUs. So you can see in this GPU system, I have given more space to ALU and less to the control unit and cache and other part. That's why GPU is much more faster compared to CPU. But CPU is giving instruction to the GPU to run a particular large language model, or how the large language model is going to be executed in the GPU, that will be instructed by the central processing unit. So just I have given a clarity that why people are focusing on GPU, whether it is in education domain or in healthcare domain, everywhere the amount of the data is very huge. When you want to process such particular data, you need GPU rather than a CPU-based system. Now, if you know that day by day nowadays we are using cloud-based services, right? All of you are using Google services like Gmail. You are using, let's say, Google Photos. You are using Google Map. You are using Google Drive. You are using Google Photos. A lot of services that are provided by this Google, which is a cloud-based platform that you are using. So somebody will say that if you cannot have sufficient, you don't have sufficient amount of resources, then why you don't go to the cloud? Like Gmail case, you know, Google email case, you know, you are not keeping anything into your system, right? Suppose I will provide you my system, you will enter your username and password, you will be able to see your email. So nothing is stored in your computer system. Everything is stored in the cloud. Similarly, as large language model require large amount of GPUs, if large amount of GPUs are not affordable by a human being or a particular person, then we will depend upon the cloud, because cloud case it is cheaper, right? We are getting Gmail service or Google services up to 15 GB it is free, right? So no charge is given up to 15 GB. Only if it is exceeding 15 GB, then only you are going to pay for it. So that is one of the solutions. Cloud-based solutions can be provided, or there are many companies that are providing you paid services to run the large language model. That is one solution. Another solution is that if I, in a particular organization, let it be at NITW, I want to run my large language model, which I want to provide to all the educational institutions. Like anything you want to ask related to engineering, science, technology, management, these can be answered by that particular large language model. So I have to buy enough number of GPUs. Until unless I get enough number of GPUs, even if you type something from, my LLM is not going to process, because inference process will be low if the less number of GPUs are there. So buying the LLM is a solution, but it is not affordable by all type of organization. Maybe higher learning institute can go for many GPUs. But when you talk about a school cannot go for a multiple number of GPUs to provide the inference services. So the solution is that, as I mentioned, DPIN, which is called as decentralized physical infrastructure network, that can be used because in that case many people are using the services without paying a much amount. One of the example is that all of you know about one of the very well-known project called as weather forecasting. Every day you are getting message that whether there is a rain in your place or not. Okay, nowadays weather forecasting system is much mature, and it is also stating that after 2 hours there may be heavy rain. So you are getting this weather forecasting, okay, of let's say 24 hours or 2 days, or let it be half day or whatever maybe. You are getting this system because of these computational resources. Without computational resources, it is not possible for you to predict that whether in this particular location whether there is any rain or not. So in that case, there is a platform which is running behind this particular project. And if you will surprised to know that the resources that are used behind this weather forecasting is not owned by a single organization. Imagine, predicting the climate is very difficult. How much data you have to deal with, but processing this particular data and providing such kind of warning messages that there is a rain, it is not a easy task. You need so many computational machines, but without that so many computational machines, this project is able to do that. Then who is providing this one? These resources are provided by the common people. Like if your computer system is free, and you can share your resources to that particular platform. If you are busy, then you are not going to provide resources to that particular platform. And more than 10 lakh users are active at any point of time to provide these resources to this particular platform, so that the weather forecasting project can do that particular work. In the similar fashion, if GPUs are there, GPUs are available across the world, right? Whatever GPUs are available across the world, whenever these GPUs are not used. For example, nowadays many people are playing game. They are using GPUs, but they are not using GPU for 24/7. Or there are many people use GPU for video purpose and photo purpose, or designing different kind of e-materials. They are using that, but they are not using the system for 24/7. So what we can do, if a system is not available for 24/7, okay, not required to use such resources, we can provide to run the large language model for a particular domain. Okay, so this is called as untapped GPU computing. Untapped means when you are not using, you are donating this particular computational cycles to a particular system. There, large language model plays a very important role. Now, when you go for decentralized, why we call decentralized? See, if I go for a centralized system, I will take a group of GPUs, put in a centralized system for developing AI in education. If there is a natural calamity happen, or if there is a power failure, or if there is a hardware failure, or intentionally somebody has done something, then entire things is going to be collapsed, because it is a centralized system. So centralized systems are prone to single point of failure. If something happened there, the entire network is going to be collapsed. That's why nowadays people are thinking about a decentralized way of serving a LLM. Decentralized means one may be at, let's say, India, another may be at US, another may be at UK, another may be at Japan. All these things need to be connected together to provide the services. So in that case, you need not depend upon any centralized system. Okay. Again, you can see, if I consider the GPUs across the world, we are not following the same time zone. So like in India, this is a night now, a night time. US, it is a daytime. So at any point of time across 24/7, you will get computational resources to run the large language model. That is the advantages of going for decentralized physical infrastructure network. And we are using this ideal GPU resources. We are not using dedicated GPU resources, right? Now somebody will say that if I have a GPU, if you want to run this large language model for education, why I'll donate my GPU? why I donate my computational device, why I donate my computer resources, laptop or desktop, whatever may be. Because with respect to that, if you donate based upon the usage, you will be rewarded. You will be given some money, right? If your computer system is idle, if somebody is using your system, then they have to pay for it, right? So owners are happy because owners, the resources are complete idle. Now, as the resources are idle, now they are getting some amount. They are also happy. And being a LLM, I want to run my LLM. So for that also, I cannot afford a large amount, but I can afford a very nominal amount that can be affordable. So from provider's perspective, it is also a good solution. From consumer perspective, also it is a good solution. So DPIN is used for running this LLM inference services. Now, you talk about chatbot. Like many times we want to develop a chatbot for education system. What the chatbot will do? Chatbot will give some kind answer, some basic queries. Like many websites, you talk about IRCTC. Also, some chatbot is there. If you want to cancel the ticket, if you want to let's say change the name of a person, these type of basic queries that are available in the chatbot. And chatbot is an interactive application. Interactive application means whenever you will ask a prompt or ask a query, it has to immediately respond. If it is not immediately responding, then that is of no use. That is not an interactive application. So timely response of everything is more important. Even if we implement this LLM in education system, we have to ensure that whenever a student is asking some query in personalized learning, so the LLM will able to answer this within a particular time frame. If LLM is responding after 1 hour, then nobody is happy with that type of particular system. So low latency is required. Low latency means low delay. Without any delay, you have to answer the questions, right? And this is a memory intensive applications because see how many materials are there. There are a lot of materials are there. From these materials, based upon the need of the student, you have to identify and you have to answer that particular question, right? So this is called as a memory intensive application. It is not a CPU intensive application. You have a large memory. In that memory, you have to train your model, and based upon the query of the customer, you have to respond to that particular query. So sometimes what happens, if you have given a very large task, somebody can give a small task, somebody can give a large task. So one particular task may not fit in a particular GPU. Don't think that GPU can solve any type of inference. If you give a very complex task, right, which is very complex in nature, so one particular GPU is not capable to answer that particular task. In that case, what we are going to do? We have to use more than one GPU. Okay, suppose a user requirement is let's say 2 GB, but let's say capacity of a particular GPU left with 1 GB, so it cannot process your particular task. So in that case, you need multiple GPUs to fit a particular type of task. Now, many people have thought that you are not only going to implement this LLM for a single student, you have to implement it for a large set of students. The number of students are in millions, okay, millions. So you have to answer the query of millions people per second. So how to process these millions queries in a particular system? It is also challenging. Like if millions user, if one user require 1 GPU, I need 1 million GPUs to run my services. So many people have come up with the process of pipelining. What do you mean by pipelining? Like even a computer, if you take an example, if I want to read a particular information, read takes time. Once I read a information, I am going to execute something. It also takes time. When I execute, I am going to write that particular information. So for every page, you are sparing one particular page. Each page takes some amount of time. So if I go for process of pipeline, multiple inferences can be done at the same time. I'll show you a simple example you can understand. Like you can see, this is let's say student one. This is you consider as a student one. Now student one, let's say there are 4 different phases. One is I have to fetch the information. Another is I have to decode the information. I have to execute it and I have to write it. So when the first student is entering into the a particular system, it is in the fetch stage. Okay, while the second, third, fourth, fifth student has not entered to our student, not entered to our system. Now, when the second student, okay, is entering into the system, then first student is moving from fetch stage to decode stage. Okay, it is decode stage. At that time, second student is entering into fetch stage. Means when one person is available in the decode phase, and then one person will be present in the fetch stage. In the next cycle, somebody will be there in the execute stage, somebody will be there in the decode phase, somebody will be there in the fetch stage. Similarly, in write wake also, when one student will be there in the write wake phase, another will be there in execute, decode, and fetch stage. That means multiple inference services that can run parallelly through this process of a pipeline. That is the advantages of going for the pipeline. But challenging part is that when you are accumulating multiple GPUs to implement a particular system, do you think that all the GPUs are having similar configuration? Like take in this program, more than 250 participants are there. If I ask you, how many of you are having similar type of computer system? Whether we all have same type of computational system? The answer is no. Like you may connect with a mobile. Mobile has different configuration. Somebody is connected with laptop, different configuration. Somebody is having desktop, is having different configuration. So everybody is connected with different information, a different configurations, and they have also different type of informations they want to set. So what we can do, if I want to go for this inference services vary with respect to the GPUs. Like if I run in one GPU, it will take different time. It will run in another GPU, it will take another time, right? Like you can also see sometimes we write a computer program, and if I run that computer program in one system, it is taking, let's say, 10 seconds. Another system, it is taking 20 seconds, because the computer capacity matters when we run this particular code, right? So that shows that a heterogeneity of the system. Heterogeneity means everybody is having different configuration. Inference services are different. So mapping of these inference services started by the user or the student to the GPUs is quite challenging. Now I'll show you a practical example. There is a large language model that is called as Llama 2. Okay, if you know about large language model, you know about this very famous model that is called as Llama 2. This Llama 2 model is coming in 3 different variants. One variant says that Llama 2 with 7 billion parameters. 7 billion parameters. Another is saying 13 billion parameters. Another is saying 70 billion parameters. So obviously somebody will say that if I take this 70 billion parameter, it is much faster. It is giving more appropriate content compared to 13 billion or the 7 billion one. Like last lecture also, one of the participants asked about some mathematical questions, right? So with the current model, how many with the current model, whatever maybe the billion of parameters are there, it is not fulfilling your request, or it is not giving the correct result. But when this 70 billion is going to increase to, let's say, 100 billion, or let's say 200 billion or 500 billion, maybe it is going to give you a perfect result, right? So the issue is here that is Llama 2 model comes in different version. If I take the very famous version, that is 70 billion. So if I, like, ChatGPT is a platform, behind that what we have? We have a large language model. Let's say the large language model is the Llama 2 model behind the ChatGPT. So this Llama 2 model with 70 billion parameter needs 130 GB of memory. If you want to run this particular model, you need to buy a GPU having 130 GB of memory. Okay, 130 GB of memory. But if you see, there is a very famous GPU called A100. The GPU name is called as A100. If you talk about A100 GPU, A100 GPU is having only 80 GB of memory. Okay, your computer is, let's say, 80 GB of memory. You want to run a model which is of 130 GB. Is it possible? It is not definitely not possible, because if I have 80 GB, I can accommodate maximum of 80 GB. If it is exceeding 80 GB, then I am helpless. So the problem with this particular model is that if I take a A100 GPU, which is a general purpose GPU, normally people use it, right? It is not a specific one. It is not able to accommodate our Llama 2 70 billion parameter large language model. So this model cannot fit in a in this particular GPU. Then what is the solution? So somebody will say that I will take two A100 GPU. Is it possible? Yes, it is possible. If I take two systems of 80 GB each, so together I have 160 GB, and my requirement is 130 GB, so it can be fulfilled. That is one of the solution. But in many cases, like when you go for education system, maybe when you talk about a school children, the task is very simpler, right? They ask the question which is very simple in nature. But when you go for a higher learning system, okay, in that case, the task is very complex, like solving a mathematical equation is also very challenging part. So in that case, if you need larger memory, one particular GPU is not able to answer your query, or it takes a lot of time to answer in that particular GPU. So you need multiple systems together to provide different type of services. Now, if you go for different type of services, nowadays people have thought of blockchain, right? Like I told you that I am a user, I want to run a large language model, I am ready to pay, and there is a provider who is having enough number of computational resources, and that person is ready to give me that particular resources. So when payment is coming to picture, come into picture in the large language model, people have integrated blockchain. What blockchain is going to give? Blockchain is providing with transparency that whatever amount you have paid, the same amount is credited to the provider. So that way we can trust this particular system. Okay, so it is a different topic that deviates from our discussion. So I am not going in details about this particular system. Now, what Llama 2 model is actually doing, what large language model is doing, the main purpose of this large language model is to generate the content. So it will take the first your prompt. Based upon that, it is generating the first token, second token, third token, fourth token, up to nth token. Until unless the user stop, or until unless the answer response is completed, it is go on generating different type of content. So when it is taking different type of content, like sometimes we write there, PHERE there, right? When you write there, everybody is guessing that the next word is. When I'm typing I, the next word is M. So these are the common words. So whenever this type of models are used, as there is used, after that is used, I is used, after that M is used. So these two are considered as a single token to guess what may be the third word. So that type of generations are token generations are done by this particular model. Like if you go for the Llama 2 model, they are using different decoding procedures, which is called as auto decoding procedures. Auto decoding procedures are also used in this weather forecasting kind of thing, or statistical analysis, to guess what is going to happen in the future based on whatever the data available with us. I am going to predict what is going to happen in the future. Now, if you go for any type of model, you go for any large language model. So every model has three different layers. First layer is called as input layer. First layer is always called as a input layer. Second layer is always called as hidden layer. And the last layer is called as your output layer, right? You take any model, whether you take Llama 2 model 7 billion parameter, or let's say 70 billion parameters, whatever may be, it has three different layers. Any neural network you take, it has three different layers. So first layer is also called as embedding layer. Why I am talking about these layers? Because when you generate the content, you should know that how these contents are generated. Contents are generated with respect to the layer, right? So for example, I have taken this is input layer. This is a neuron, this is another neuron. This is input layer. Let's say I am taking two hidden layers. Okay, these are the hidden layers. And this one is considered as output layer. Now what happened? These layers are connected like this, right? These layers are connected like this, okay? Something like this, right? Now, the first layer is called as embedding layer. Embedding layer is responsible to generate the token. Hidden layer is also used to generate the token. Output layer is also consolidating these tokens and displaying the response, right? So any type of model you are going to use, you have three different layers. One is the embedding layer, transformer layer, and output layer. So whenever a new token is generated, we consider that what we have generated previously. Based upon that, we are going to generate a current token. And once a current token is generated, I am again embedding that current token into the existing token, and I am generating a new token. Like whenever you go for a time series kind of data. For example, if I say 1, 2, 3, what will be the next value? Then you will say next value is 4. Then I'm taking this as input. I'm guessing the next one. So guessing next one is, let's say, 5. Then I'm taking that this is my input. Like that, I'm gathering different inputs, and based upon that, I'm going to analyze it. Okay, just a minute. Okay, sorry for interruption. So what I mentioned that if take any type of neural network, in every type of neural network, we have three layers: input layer, hidden, a set of hidden layers, and output layer, right? So here we call that as the embedding layer, transformer layer, and output layer. Every layer is generating different tokens. So they are combining what is generated to create what is going to be generated next. Like if you take a existing chart, right? Everybody is using chat GPT. You are using existing chart. In existing chart, whatever conversation you have done, now if you put a prompt, your response will come based on your previous conversations also. But if you delete that chat, you start a new chat. You start a new chat, and if you put a particular prompt, it is not related to your previous prompt. So every time it is depend on what conversation you have made earlier. Like if you ask about education, all the prompt whatever you are going to give, it is going to show with respect to education. Somebody is asking let us related to the computational devices. So whatever prompt it is going to give, it is going to relate it to the prompt related to the computational devices. So based on your previous conversations, it is going to generate what it is going to generate in the future. So I am showing you this diagram. This diagram will give you a correct picture, right? Like here you can see there is a user, right? There is a user who put a prompt. User has put a particular prompt. When user put a particular prompt, it will go to which layer? First one is called as embedding layer, right? But running this particular embedding layer is challenging, right? Who is going to host this particular layer? Like if you develop a particular model, you will run in your computer system only. Whether you use a CPU or a GPU, you have to use that. So we are going to use the embedding layer. Once embedding layer generates some particular token, right? Then it is transferring it to the first layer called as transformer 1 layer. Similarly, it will go to transformer 2 layer, transformer 3 layer. Like that, it will go for transformer 40 layer, right? And you can see there is a GPU which can handle all these layers. Every GPU is having a limitation. Assume that this GPU is only taking care of the input layer and 40 transformer layer. And once it is handling this, its capacity is adjusted. So I cannot use this GPU to run the rest of the layer. So I need an additional layer. Sometimes a task is very big to fit in a particular GPU. Sometimes multiple layers can fit into the GPU, but it is not the whole model can be shipped in that particular layer. Like as I mentioned that 130 GB is the requirement of this Llama 2 model, but our GPUs are having let's say 80 GB or 70 GB, something like that, 80 GB. So that particular GPU cannot satisfy, right? That GPU cannot satisfy. So 80 GB, if it is there in a GPU, I'll try to accommodate this out of 130. I'm going to, let's say, give 80 GB to that particular GPU. Remaining 50 GB, I'll give to another GPU. So that combinedly 2 GPU can perform this particular task. Like here you can see there is another GPU which is having a transformer 41 layer to transformer 80 layer and output layer which is executed in this particular GPU, right? So one GPU is taking care of 41 layers, another GPU is also taking care of another 41 layer. And what actually they are doing? They are generating different words. Words is called as the tokens. And once it is done, then again it will go to the it will go to accept another prompt. Like whenever we generate a particular response, ChatGPT is again asking to give another prompt. When you give a prompt, again the same process is repeated. So this process can be done in parallel, right? Because multiple users are accessing and every user is also giving multiple prompt one after another. So we need parallelism to do particular task, right? So when we talk about the parallelism, parallelism can be done within a particular layer. Parallelism can be done between different layers. So based upon that, there is a interlayer parallelism and intralayer parallelism that is done in the large language model to make inference services as faster as possible. Okay. Now you can see an example I have given here. Suppose you have developed, you have taken a large language model which is having 48 layers. Total number of layers is 48. And let's say number of GPUs that is available is 4. Total number of GPUs is 4. And if I assume that these GPUs are of same type, let's say 4 GPUs of same type, then every GPU is responsible for how many layers? 12 layers. First GPU is responsible for 12 layers. Second GPU is responsible for 12 layers. Third is for again 12 layers. Fourth layer is in 12 layers. So they can divide this particular model into 4 different parts and individually 12 in each bunch of 12 layers can be executed in the GPU. Somebody will say that why don't you assign more than 12 layers into a GPU? Because every GPU is having also a limited capacity. I cannot exceed that particular capacity. So that way we can solve this particular type of problem. Okay, you can see here that I want to generate the tokens, right? Tokens means words, right? So you can see 1 to 256. First 256 tokens are generated by a machine. Another 256 words are generated by another machine. Another 256 is generated by another machine, like that. Okay, we are taking 256 ones because I am assuming all are generating the same type of token. But practically it is not true. They can generate any number of type of tokens to do this one. So in this way, I can introduce different micro batches, and these batches can be assigned to the GPU to process these informations. Now you can see, right, multiple GPUs are engaged to do the inference services, and multiple users' answers can be given by using this step-by-step process. Okay, many people have also think about how to implement a different device level LLM. Like if you talk about mobile device cannot keep the data for longer period of time, right? Mobile devices, we cannot keep the data for longer period of time. If you talk about smartwatch is also a computational devices. It cannot keep the data for longer period of time. So keeping the data for longer period of time is always a challenging part because everybody is having limited amount of memory. That's why people have thought of why don't we go for lightweight LLM. Okay, what is lightweight LLM? I am training some kind of model, right? And based upon the training, I am generating some kind of, let's say, pre-trained model, and that model can be given in the devices so the device can perform different tasks, right? Like here you can see, I am showing you different device LLM. These are nothing but icons of LLM, but this is done in the device level. Somebody will say that I have enough amount of storage. You can go for cloud-based LLM. Okay. Somebody will say that I don't have enough resources. Then you can for edge-based LLM, or you can go for device-based LLM to generate different type of text. So this is one of the example you can see, and you can see there are different type of models are running in different layers to provide different kind of solutions. Now, yeah, again, device-based LLM, you can see I can take a mobile in which I can perform this LLM. I can take a laptop where I can do this LLM services. Or if I talk about a vehicle, smart vehicle, There also I can give some kind of LLM. Like a driver wants to ask some kind of query. There also I am going to provide some kind of solutions. So starting from a very small device to a very large devices, we are going to implement different level of LLM. Now you can see when you look into implementing this LLM for education system, you can see that total number of type of combination of these LLMs is considered as 6 type. What is the meaning of this one? It says that if you go for the first one, there are 6 different communication mechanisms which can be implemented for education system. First one says that I have very small models. These are nothing but very small model like machine learning based model. They are not complex deep learning model. They don't need a big amount of resources to do it. So I am integrating various small model, and these models are also not running in a single location. They are located in different location and they are running this one. So it indicates that these are the small models. They are integrating together to perform this one. For example, for a school system, I can develop one. For a higher secondary, I can do this one. Or for, let's say, engineering management, higher education, I can implement this one. But these small models are coordinating each other to provide the responses. That is the first type of model. Second type of model, you can see, these are not large language models. These are, you can say, small language model. This is not a large language model. Now, B picture, you can see these are the symbols of large language model or ChatGPT, right? So I am integrating different decentralized large language model. Every large language model is, let's say, responsible. Every LLM is responsible for a particular domain. Like I told you, for school domain, I will go for a large language model. For, let's say, 6th standard to 10th standard, I am going to do one. Or let's say 10th standard onwards, I will take another LLM. They can be also integrated. They can communicate each other to provide the response. Like whenever a prompt is coming, one particular LLM has to decide whether it can give a response or not. If it cannot give a response, it will redirect to other LLM who is responsible to do that one. So in that way, we can solve this particular problem, and it will not a burden to a particular large language model, right? Now, if you go for third one, here you can see I am using LLM. I am also using a local model. Like I can develop a large language model, but if you go for like a particular type of education, like last lecture also I told you, designing a large language model for education system is challenging. Designing a large language for the person with disability or person with learning disability is also challenging, right? So when you talk about a specific case, specific type of students or slow paced students, in that case, you need to integrate large language model with the local models. So I told you here, these are the local models. Here, along with this large language model, I have integrated what? The local models. That is another type of communication mechanism. Now, coming to the fourth communication mechanism, in this case, we have a centralized LLM. Centralized LLM means whenever you make a prompt, right? It will reach to this particular system. This system has to analyze whether LLM 1 is going to answer this, or LLM 2 is going to answer this, or LLM 3 is going to answer this. So different people can give different options, right? Well, all the requests are going to reach to the same system, right? That system has to decide that whether I want to go for first LLM or second LLM or third LLM. That way I can decide. Now, coming to this one, it is also centralized one, right or no? This is also centralized one, but it is not dealing with large language model. It is dealing with the small language model. Okay, this is dealing with small language model or this local model, but it is centralized. That is also one type of model. And the fourth model is the combination of all the previous 5 models. It is centralized, okay, but it is taking hybrid models. Hybrid models means it is taking large language model as well as local model to perform the particular task. Now, when you are going to implement it, you have to use one of these communication mechanisms. Obviously, based upon the feasibility, we can think that whether to go for a local based model or LLM based model or a hybrid model. right? It depends upon what kind of things we are going to apply. What is our adaptability? Which system is more suitable for a particular type of education, that we can discuss. Next is that here you can see there are different people has given different task description. Right? I have given some task description. I ask my LLM to give a particular response. Right? This, for example, this particular example is given in terms of UAV. UAV is called as unmanned aerial vehicle or drone. Nowadays we are using drone, right? So suppose somebody wants to use a drone to capture some of the images of a particular location, right? Then I need to say that what is the coordinate of that particular drone, right? What is the coordinate of a particular location? Based upon that, I am going to give some kind of response so that this drone can capture that particular informations in a particular location, right? So you can see we asked a cloud-based LLM to answer this one. In fact, that cloud LLM is again, if you are submitting a very big task, that is again decomposed into different subtasks, and these subtasks are given to different LLM. Like I told you here, that there is a centralized LLM. When you give information to a centralized LLM, it is decomposing your task and it is giving to different LLM. Like if I submit a request here, the request can be divided into three parts. First part can be executed here, second part can be executed here, third part can be executed. This way we can solve this particular type of problem. Now this is the process. You can see there is an end user who is asking that can A replace B at time T? You have developed some kind of schedule. Okay, like I told you, tutor can make a schedule. The learner or the student can make a schedule. We have to make sure that these schedules are not overlapped each other. So assume that there is a event A and there is a event B. I am asking that I want to replace the event A with event B at a particular time instance, whether we can do it or not. So what we are going to check? We are going to check that whether A and B, they are independent or disjoint or not. If they are disjoint, then only you can do it. For example, a teacher wants to take a class from 12 to 1. Another teacher wants to take class from 3 to 5. There is no overlapping. So it is possible to overlap. It is possible to swap A with B or replace A with B. But if the class is overlap, like one is 12 to 1, another is let's say 11:30 to 12:30. In that case, there is a conflict between these two events. So such type of events cannot be replaced. Like in the previous session, Madam has explained about explainable AI. Here also you can see when such type of models are there, there is a explainable AI mechanism which explains that why A cannot be replaced with B. Or if A is replaced with B, why it is feasible. Whether it is a feasible or infeasible, it is giving you an explanation why that decision is given by a large language model. So that way, the large language model can ask different type of query. Now, when we are talking about a large set of inference services, like many systems are going to be, many students are going to use the system, right, for inference services. So there may be a load balancing issues, right? Load balancing issue means one is overloaded with, let's say, 100 students inference services, while another machine is idle without executing any inference services. So there the load balancing come into picture. Like you can see here, like in this case, you can see the load of this particular machine is up to this point, but load of this particular machine is up to this point. So I can say the first machine is taking so many inferences, so many prompts compared to the second machine. So if we have a load balancer, we can decide that how we can give equal load to multiple GPUs. Similarly, there is a defragmentation process. What defragmentation process is that? Fragmentation means I am going to divide. Fragmentation means if I divide a particular task into subtasks, that is called as fragmentation. Defragmentation means you cannot do it, right? Like there is a inference services which is very complex, which I want to assign to this particular machine. But this machine is not able to accommodate it because you can see the load is up to this much. Let it be 35%, and rest 65% only I can use. Rest 65% I can use. but let's say this request require more than 65%. So it is possible if I move this particular load to another machine so that it can be accommodated. Like that, there are several approaches are there which can be used for managing the load of different GPUs. Okay, so these are the different mechanisms which you have. I am not going in detail about these mechanisms, right? Now coming to the scheduling problem, right? So our objective is that there are n different machines are there. Okay, n different GPUs are there. I am assuming these GPUs are nothing but M1, M2 up to Mn. Each M is representing one particular GPU. Now I have a large language model with k number of layers. Okay, let's say each layer is representing one inference service of a student, right? Now I need to map these k number of layers into n different machines. Okay, every layer is responsible for generating some tokens, right? They need to generate these tokens using the GPUs only, right? So there is a need of mapping the k layers into n different machines. So the definition of this particular problem is divided into 4 parts. First part says that how much time it is going to generate a token in a particular machine. You have given me, let's say, one particular task. As a user, you asked me a particular question. How much time I am taking to answer that particular question is considered as layer computing latency, right? Another is that if a particular machine is overoccupied or exhausted, like 80 GB is the space, 80 GB is fully occupied for a A100 GPU. Then what you will do? You will consider the remaining layers in another GPU. If one layer is exhausted, then I need to focus on other layer. So in that case, we can think about the communication latency. So one is called as computing latency, another is called as communication latency. Whatever you are doing in a GPU is considered as computing latency. And once you complete it, you are transferring the result to another one. The time required to you transfer this one is called as communication latency. So how latency can be minimized? Latency can be minimized if you reduce the computing latency as well as the communication latency, right? Somebody is giving a response. You need to process that particular response, right? Okay, or query or a prompt, you need to process it. If the processing time is minimized and responding time is minimized, then we can say inference services can be faster. But if you want to run multiple layers in the same machine, I am running, let's say, multiple layers in the same machine because that machine is such powerful, it can execute any number of layers. Then the communication time is considered as 0. Like if I am running 2 different tasks in the same machine, the communication time is considered as 0. Third one is considered is that how much GPU memory is remaining. Because before assigning any task to a particular machine, I need to ensure that some GPU memory is available. If GPU memory is available, then only I am going to process it. Otherwise, I am not going to process it. Another thing is called as layer memory requirement. Every layer has some memory requirement. I consider layer means whatever the task is given by the user or a educator or a listener or you say a learner or a student. Whatever task they are giving, that is considered the memory requirement. So if remaining GPU memory is more compared to the layer memory requirement, then only I can accept it. If it is not, then I am not going to accept that particular request. So it introduces a problem that I need to assign these layers to the machine. I want to create a assignment sequence that which layer is assigned to which machine such that the time required to generate these tokens, which I told you initially as TPOT. TPOT is called as time per output token. How much time it takes to generate the first token, how much time it takes to the second token, how much time it takes to the nth token. So if I can minimize that particular time, then that is definitely a best one. That is called as a TPOT. So, but the condition is that at any point of time, whatever memory is there, like I told you, GPU is having 80 GB of memory, but my layer requirement is 130 GB. So I cannot satisfy because 80 is not greater than 130, right? But if I have 130 GB of remaining memory and 80 GB is considered as a layer, then it is satisfied. So this way you can set up this particular problem, which you can address layer by layer. So there is a problem which is called as NP-hard problem in computer science, okay, or in mathematics. NP-hard problem means you cannot solve this problem in polynomial time. And sometimes this problem, if you want try to solve, you may not get a solution in your lifetime, right? For example, I'll ask, let's say there are 512 number of students. Assume that we have a 512 number of students, okay, and there are 16 teachers in a particular class or a particular institute, okay. There are 512 students. They need to assign to 16 different teachers for some kind of project assignments. So how many ways we can assign these 512 number of students to 16 teachers? Can anybody tell? If I want to assign 512 different students to 16 different teachers, okay, then how many ways I can assign this 512 student to 16 different teachers? Can you write in the chat box? How many ways we can do this? So if you find the number of ways, it will be 16 to the power 5. Okay. And you know 16 to the power 512 is much greater than 10 to the power 512. And what is 10 to the power 512? 10 to the power 512 is nothing but 1 followed by 512 number of zeros. 1 followed by 512 number of zeros. So if one solution takes 1 second of time, if you calculate 10 to the power 512 or 16 to the power 512, you will not get the solution in your lifetime, right? Even if you type 16 to the power 512 in your computer system or your mobile phone, you will not get any response. It will say that it is infinite. It is a very large number. So the problem is that such type of problems are considered as an NP-hard problem, which needs some kind of approximation algorithm rather than focusing on different usual algorithms to solve that particular problem. Now, many people suggested that why don't we convert the problem of assigning these layers to the machine into a graph problem. What do you mean by a graph? You can see here. I am showing you a graph. What is this graph? This graph is a graph is consists of some node. These are nothing but different nodes. Nodes are nothing but different vertices. And the communication between different vertices is considered as the latency to move from one particular node to another particular node, or we call that as edge. So a graph G is always represented in the form of set of vertices and set of edges. So this large language model we have converted into a graph problem. Why we converted into a graph problem? Because there are many well-known solutions that exist for this particular graph problem. If I convert it into a graph problem, whatever solution exists for the graph, same thing can be implemented for the large language model. Like here you can see, I have taken different node. Okay, and what is this value indicate? This value indicate that if I am going to assign layer 1 to the machine 1, if I assign layer 1 to the machine 1, how much time it is going to take? Similarly, if the same layer is assigned to machine 2, how much time it is going to take? But I cannot assign to both machines. I can assign to either a machine 1 or a machine 2. And once layer 1 is successfully executed, then layer 2 need to be assigned to either machine 1 or machine 2 if their capacity is not exhausted. Similarly, I am going to execute layer 3 into machine 1 and machine 2. Right? So over a period of time, if a particular layer is exhausted, okay, if a particular layer, when it is assigned to a machine, the machine is exhausted. Like I told you, 80 GB is exhausted. Then you have to bound to use other machine. Right? If machine 1 is exhausted, then I need to think about go for the another machine, that is machine 2. Or machine 2 is exhausted, then I can move to the machine 1. So what these values indicate? This value indicates that how much time it is going to take to process that particular program. Because our objective is to reduce the inference time. Reducing the inference time is coming when you are going to estimate how much time it is taking for computation, how much time it is taking for communication. If computation time, communication time is reduced, overall time is going to be reduced. So for example, if you can see here that when the layer 1 is assigned to machine 1, it is taking 15 units of time. When the same layer is assigned to machine 2, it is taking 16 units of time, right? Same layer with two different machines, because both machines are having different configurations, so they take different unit of time. But when layer 2, and you cannot execute layer 2 until unless layer 1 is completed, because if layer 1 is generating the first token, layer 2 is generating the second token, layer 3 is generating the third, like that, right? Now if I go for layer 2, layer 2 is taking 5 units of time in machine 1 and 6 units of time in machine 2, which you can find here. 5 units of time here and 6 units of time here. Similarly, layer 3 case also it is 5, 6, which you can find here. Now, if they are assigned to the same machine, they will continue. If they are assigned to different machine due to shortage of the GPU resources, then you need move from one GPU to another GPU. For example, if I am executing some layer in machine 1 and subsequent layer I am executing in machine 2, you have to pay the communication latency of 20. Similarly, if I go for machine 2 to execute some layer, and if I go for machine 1, then it is taking 20 units of time. That you can see here. This 26 is considering 6 units of time to execute in the machine 2. 20 units of time is required to move from machine 1 to machine 2. Similarly, if I move from machine 2 to the machine 1, this 25 indicates 20 time it is taking in the communication, 5 unit of time it is doing in the computing. So it is calculating the computing time, it is also calculating the communication time. So these are showing the computation time and whenever required, computation plus communication time when there is an exchange in the machine. Now we can make an inference faster if we traverse from layer 1 to, let's say, layer 3 without any delay. If I go very fast, then only when I go for this particular process, then it will be much easier. But if it takes, if I'm consuming more time, or if I have a slow computational devices, it will take a lot of time. So in order to make the inference faster, you have to see that there should be a shortest path from layer 1 to layer 3. Like in real life also, suppose somebody wants to travel from Warangal to Hyderabad. Okay, Warangal to Hyderabad, there may be a number of paths, right? There may be a path without toll gate. There may be a path with toll gate. There may be a path which is redirecting through some village areas. So you need to decide that which particular path is suitable for you. Right? For example, if you go with toll, then you can reach to your destination much faster. So you may find different path. For example, you can see here, like I can follow this particular path to reach layer 3. Somebody can say that I can follow this particular path to reach layer 3. Somebody can say that I will follow this particular path to reach layer 3. So you may find number of paths. How to find an appropriate path to reach to a destination? That's why many people have come up with different solutions. It is a mathematical solution, right? For example, somebody will say that pick machine 1 for layer 1. Okay, and pick also layer 2 of machine 1 also you can use for layer 2. But let's say layer machine 1 is exhausted, so layer 3 need to be executed in the machine 2. So this way we can make a solution. Now you can see here. So this is a theoretical things. I'm not going in detail, right? Okay. So this is the algorithm normally followed to convert a large language model into a graph problem, and through that graph problem we can solve this particular problem, which I discussed the same thing I have written here. Okay. I'll show you a simple example so that you can easily understand that how actually this process is carried out. So let us see a very simple process. Assume that you have 3 different GPUs. Okay, I have represented these 3 GPUs as GPU1, GPU2, and GPU3. I have 3 different GPUs. And I have a large language model with, there are, let's say, 3 layers. Normally, large language model has saved so many layers. But for easy illustration, I considered only 3 layers. Now, these are the requirements of these layers. I cannot assign a layer to a GPU if the requirement is not satisfied, right? Every layer has a requirement. Like every student has some requirement, every person has a requirement, every user has a requirement. Every layer is having some requirement, and every GPU is having a capacity. Every GPU is having a capacity. We cannot exceed that particular capacity. For example, for easy illustration, I am saying what is the requirement of this particular layer? Requirement of this layer is 2. But what is the capacity of GPU? Capacity of GPU is 5. It is in some memory unit. I am not saying MB or GB or something like that. So edge 2 is less than equal to 5, or 5 is greater than 2. So GPU 1 can execute layer 1. Similarly, GPU 2 can execute layer 1. GPU 3 also can execute layer 1. Why I am saying this one? Because my requirement is 2, but these GPU's requirement is 5 or more than 5. That means the requirement can be satisfied by 3 different GPUs. So which GPU I will choose? That is more important. I will choose a GPU which takes less time. That is the obvious one. Anybody can say. So you can see, if I assign to GPU 1, it is taking 1 unit of time. If I assign to GPU 2, it is taking 10 units of time. But if I assign to GPU 3, it is taking 1 unit of time. Now you tell me, which GPU is suitable for my layer 1? So obviously, you will say that the less time is taken by GPU 1 or GPU 3. So you choose either GPU 1 or GPU 3. So that here you can see, I have assigned GPU 1 to the layer 1. Okay, so layer 1 is going to be executed in GPU 1 to generate a set of tokens. Okay, minimum number of token is 1. It can generate any number of tokens based upon its capacity. Now, once I assign layer 1 into GPU 1, what is the requirement of layer 1? Requirement of layer 1 is 2. But what is the capacity of this GPU? Capacity of the GPU is 5. But 2 unit is consumed by this layer 1. So I left with only 3 unit. I left with only 3 unit. Right? Okay. So remaining capacity of this GPU 1 is 3. Now what I'll do? I'll proceed with layer 2. Right? What is the requirement of layer 2? The layer 2 requirement is 4. Layer 2 requirement is 4. But what is the remaining capacity of GPU 1? Remaining capacity of GPU is 3. So is it possible to assign this layer to the GPU 1? The answer is no. You cannot assign. Why you cannot assign? Because my requirement is 4. I'm asking 4 GB to someone, and that person is having 3 GB. So GPU 1 is not capable to run layer 2. But GPU 1 is capable to execute layer 1, and it is taking 1 unit of time. Right? Which I call as TPOT is equal to 1. Now GPU 1 is exhausted. GPU 1 capacity is exhausted. So what I'll do? I need to think about going for other GPUs. What are the other GPUs we have? We have GPU 2, we have GPU 3. But we'll check that whether they can satisfy the requirement or not. So if I see with GPU 2, the capacity is 4, but GPU 2 is having a capacity of 6. So obviously, if GPU 2 is having capacity of 6, we can satisfy that. GPU 2 can satisfy because GPU 2 is having 6, which is much greater than equal to your 4. So I am assigning layer 2 to the GPU 2. Layer 2 can be executed in GPU. But what is the problem? The problem is that I can transfer the result of GPU 1 to GPU 2. I can transfer my transfer the result of layer 1 from GPU 1 to GPU 2, because layer 1 is executed in GPU 1. So GPU 1 is having the result of layer 1. Once layer 1 result is available with me, then only I can go for layer 2. But this layer 2 is not executed in the same GPU. It is used in the another GPU. It is used in another GPU, that is GPU 2. Okay. So layer 1 result need to be transferred to the GPU 2. So it will consume some time between GPU 1 to GPU. What is the time? The time is represented here in the form of communication latency. So what is the communication latency between GPU1 to GPU2? It is 2 units of time. You can transfer from GPU1 to GPU2, but you have to pay the communication latency. So communication latency is 2, and layer 2, if it is executed in GPU2, it is taking 1 unit of time. That is also added in the TPUT. So TPUT for layer 1 is 1, TPUT of layer 2 is 2 as well as 1. So this way the layer 2 can be assigned to GPU 2. Okay, this way we can solve this particular problem. Now I think about layer 3, right? What is the requirement of layer 3? Requirement of layer 3 is 2. What is the remaining capacity of GPU 2? Once I switch to GPU 2, I will continue until unless that GPU is exhausted. So I am going to assign this layer 3 to the GPU 2. So which is exactly matching the requirement. Okay, 2 is the requirement of this layer. GPU 2's requirement is 2. So its requirement is exactly satisfied. So we can execute the layer 3 into GPU 2, which takes how much time? 10 units of time. Right? Now, if you remember, when I explained this Llama 2 model, I told you there is a embedding layer and there are different transformer layers, and at the end we have output layer. And once you reach to the output layer, like layer 3, you need to connect the output layer to the input layer, because again you need to take a prompt and you have to give the response. So in that perspective, if you see GPU1, we have started with layer L1, right? But we ended with GPU2 that executed layer 3. Now the result need to be transferred from GPU2 to GPU1. And if you transfer the result from GPU2 to GPU1, it is taking 2 units of time. So the total TPUT required for moving from layer 1 to layer 3 in this 3 GPU environment is 16 units of time. It is taking 16 units of time. And the path which you are finding is that layer 1 is assigned to GPU1, layer 2 is assigned to GPU2, and layer 3 is also assigned to GPU. So this way we can solve this particular problem. Now somebody will say that why you have selected when GPU1 is exhausted, why you have selected GPU2, why don't you select GPU3? GPU3 is also an alternative. That is true. You may find a number of paths from first layer to the last layer. So if I proceed with that, right? So when the layer is exhausted, when the GPU1 is exhausted, layer 2 I have assigned to GPU1, GPU2. So instead of assigning to GPU2, I can also assign to GPU3. So now when I'm assigning this layer 2 to GPU3, I'll check the requirement. The requirement is here 4, capacity is 5, is satisfied. I'm asking 4 units, but GPU is having 5 units, it is satisfied. And how much time it is going to take? It is going to take 10 units of time. But when you are moving one layer in one GPU, another layer in another GPU, you have to pay the communication cost. But the communication cost between this GPU1 with GPU3 is equal to 0. So in the TPOT, I have calculated 1 plus 0 plus 10. This way we can solve this particular problem. Now, when layer 2 is assigned to GPU3, till now what happened? In this particular path, layer 1 is assigned to GPU1, layer 2 is assigned to GPU3. Okay. Now, when I go for layer 3 requirement is 2, but remaining capacity of GPU3 is 1. So this requirement is also not satisfied because it is asking 2 units, but we left with 1 unit. So it is not satisfied. So what you have to do? Again, for layer 3, you have to move to GPU 2, which causes GPU 3 to GPU 2, it is taking 2 units of time. GPU 3 to GPU 2, it is taking 2 units of time. That is the main major problem. And even if you go for this particular GPU, it is taking 10 units of time to execute layer 3. Its requirement is satisfied because 2 is less than equal to 6, but it is taking 10 units of time. Right? So total TPUT in this particular path, if you proceed, it will get the path of value of 25. Earlier, if you remember, we got a path for TPUT with 16 units of time. But now we got a TPUT path of 25 units of time by assigning first layer to first machine, second layer to the third machine, third layer to the second machine. So these are the two possible paths that is possible in the case of GPU 1. Now, inference need not be started with GPU 1. Inference can be started with GPU 2 also. Inference can be started with GPU 3 also. So you need to explore GPU 2 and GPU 3 as well. So you will find a lot of path between GPU 1 to between layer 1 to layer 3. For assigning this layer 1 to layer 3, you may find numerous paths, but you will choose a path which is the minimum one. So I am not going to go details about the GPU 2. If you understood GPU 1, then you can understand GPU 2. I am directly going to showing the result if you process in different GPUs. Like here you can see. So when I analyze the optimal path, I am finding optimal path when I assign the layer 1 to GPU 1. When I assign the layer 1 to GPU 2, I am assigning layer 1 to GPU. You assign to any GPUs, I am getting an optimal path. Why I am getting so many optimal path? The reason is that I have considered in structure here with 3 different GPUs and 3 different layers. But in practical scenario, it is not true. Number of layers are very huge compared to the number of GPUs. In that case, finding the optimal path, you will find very less number of paths. Hardly you will get 1 or 2 paths. And that path you have to take to further execute the different layers in the real machines. So this type of simulations that people usually do to do the inference process much easier. So there are several approaches people have applied. I am not going in details. So this approach is called as a greedy approach. Greedy means if I decide that this is the best machine for now, I am going for that. Right? If tomorrow I decide that this machine is best, I am going for that. But finding such type of solution does not lead to a global solution. Like in an informal example to understand this thing, a person is having diabetes, right? But there is a, let's say, sweet box in front of him. Now the person is greedy, but saying that, okay, today I'll take one sweet, nothing will happen. Tomorrow again there is a sweet box. Then again the person is picking sweets from that one. So the person feels okay today, that's why the person is eating, let's say, sugar. Okay, or any sweets, right? But it will lead to issue in over a period of time. So greedy takes a decision whichever best at a particular period of time, but it is not always true. That's why people have come up with different algorithm approaches to find an appropriate path, an optimal path from layer 1 to the last layer, nth layer, with certain period of time. So various algorithm approaches are there which works behind the LLM. But although these type of LLM are really required in background to run, right? When you talk about AI in education or LLM in education, you may not visualize this thing from the front end. As a user, you will be happy whatever response is given by this LLM. But you are not going to check that what is going inside the LLM. But this, what I explained in short related to this greedy-based algorithm or the heuristic-based algorithm is that what's going behind this large language model. That is more important. How to generate this particular token. How to get the access to different memory or different different repository from which the data is going to be generated. That is the background of LLM. So you need to understand both perspectives. As a teacher, you need not only think that I will develop some kind of LLM, and if I give to my student, the student will get a response. They get personalized learning. They get some animation or gamifications, whatever we discussed in the previous lecture. So it will improve the our quality of education. That is not always true. But we need to think that whether our backbone network is supporting this LLM or not. Okay, when you are running this LLM in different scale, whether it is applicable because of the computational requirement, whether it is possible or not, that is more important. That's why always a balanced approach need to be figured out to solve such type of problem in the large language model. Okay, so this is all from my side. I'm not going in detail about the other algorithms, but this similar type of algorithms are also people have developed to implement in various domains. So I'll stop here. If you have any question, you can ask. Yeah, any participant having any question?
Dear participants, mic is enabled. Anyone can, if anyone has any question, they can unmute and ask question to the resource person. So it seems like no one has any questions, sir.
Okay, so thank you everyone for patiently listening me. Thank you to organizer for giving me this opportunity.
Thank you, sir. Thank you, Dr. Sanjay Kumar Panda, sir, for a thorough and engaging session on optimizing the deployment of large language models across multiple GPUs. You explained how analyzing different assignment paths help find the most efficient allocation of model layers to GPU resources, balancing requirements, memory constraints, and execution time. Your examples illustrated both the complexity and practicality of searching for optimal solutions and highlighted the challenges as models scale up, emphasizing that strategic resource allocation can significantly improve inference performance and cost efficiency. Although the session focused on technical foundation, these principles are essential for making AI powered educational platforms run faster and more affordably in real academic environments. Sir, we really thank for your expert insights and thank you for connecting advanced AI with the real world optimization needs, sir. Thank you so much, sir, for the session, sir.
Thank you very much. Thank you.
Thank you, dear participants.